carrying the Perseverance rover has entered the Martian atmosphere. The suspense in the control room is almost unbearable. The team has no control over what will happen in the next few minutes.
We are starting the straighten up and fly right maneuver in preparation for parachute deploy.
MRS reporting good telemetry log.
For the engineers from NASA and CNES, the French National Space Agency, this was what's referred to as the 7 minutes of terror. Perseverance had to touch down as gently as possible on the red planet.
The navigator has confirmed that the parachute has deployed and we are seeing significant deceleration in the velocity. Our current velocity is 480 meters per second.
Perseverance was carrying a dozen sophisticated instruments, which would be used by one of the most ambitious space missions to search for traces of past life on Mars.
Perseverance is now slowed to subsonic speeds and the heat shield has been separated. This allows both the radar and the cameras to get their first look at the surface.
Here the rover was less than 2 kilometers above the Martian surface. This was the last stage of the landing, and likely the riskiest.
The confirmation that the back shell has separated.
The ground station could only watch. Signals took 11 minutes to reach Earth. Either the maneuver had been successful, or Perseverance had crashed.
Maneuver has started. About 20 meters off the surface. UHF is good. Touchdown confirmed. Perseverance safely on the surface of Mars. Ready and singing the sands of past life.
That 7 minutes, I think, was the shortest and the longest 7 minutes of my life. For me, the really special moment is those few minutes after landing when we got the first picture of Mars.
All stations stand by for the image.
Wow, my robot that was here 7 months ago, that's been in space this whole time, is on another planet.
Congratulations to the mission.
This image was among the first sent from the Martian surface. The Perseverance rover was apparently intact and fully operational. The robot was tasked with uncovering the secrets of the red planet. Perseverance was sent millions of miles from Earth to help answer a question as simple as it is exciting. Did life once exist on Mars? What would the rover discover in its first year of exploration? Mars has long fascinated astronomers, but it wasn't until the 19th century when Giovanni Schiaparelli discovered the supposed Martian canals that the question raised of intelligent life on our neighboring planet first emerged. The American astronomer Percival Lowell mapped these canals, mistaking them for artificial structures built to irrigate cities that had long since disappeared. The myth of the Martian was born.
Invaders from Mars.
Starting in the 1960s, probes were repeatedly sent to explore the Martian surface without success.
C'était Viking en 76 qui a recherché.
In 1976, the Viking mission ran 3 experiments looking for organic life on Mars. They found nothing, so they lost interest in Mars for 20 years.
L'intérêt de Mars qui a duré 20 ans.
Since then, several rovers have been sent to explore Martian soil. The Pathfinder probe, carrying the small Sojourner robot, was the first in 1996, followed by Spirit and Opportunity. The last two proved that water must once have flowed on Mars. Curiosity, the big brother to Perseverance, landed in 2012. Its mission was to find out whether water could once have facilitated the development of life on the Red Planet.
Curiosity went to Mars to establish its habitability. Was Mars habitable 3.5 billion years ago? We found that yes, it could have been habitable. It had the right ingredients. So then Perseverance takes it one step up, right? And it says, okay, well, if it was habitable, was there life on Mars?
Just like for Curiosity, NASA commissioned the Jet Propulsion Laboratory to build several prototypes for Perseverance, each with different sizes and different technological profiles.
Perseverance was built based on the idea of Curiosity. We took a lot of the systems that existed on Curiosity and used that as our baseline for Perseverance.
They may look very similar, but the internal mechanics signal a new generation of rovers. Sophisticated high-tech developments. Specialized cameras, spectrometers, lasers, ground-penetrating radar, an oxygen production instrument, and a robotic arm for coring and storing rock samples.
These are extremely complex robots. There are 200 to 300 scientists behind each vehicle.
It took 6 years to develop, build it, and launch it, and then another 7 months to land on Mars. It takes an incredible amount of time to design everything, build it, make it space rated, test it, because we also have to test and demonstrate that it's going to work in that Martian environment.
Conditions on Mars are hostile to life. The biggest problem is the extreme temperatures, and Perseverance also had to generate its own energy.
The problem with using solar panels on Mars is that you're so much further away from the sun that you need a much bigger area to get the same energy as you would here on Earth. We sometimes have dust storms on Mars, and so that's often how rovers meet their demise on Mars. For Perseverance, we use a nuclear source which over time creates heat, and that heat is transformed into electricity.
This generator would ensure that the rover and its instruments could function on the Martian surface without disruption for years to come.
When we build missions like Perseverance, it's not just an American mission. So when we build this rover, yes, it's built here at the Jet Propulsion.
I developed it together with Roger Wiens from the Los Alamos National Lab in New Mexico. We were thinking about how to measure the chemical composition of Martian rocks and soil. I asked about his lab's capabilities, and he said, "We know how to make spectrometers and analyze light. What about you?" I told him in France, "We know lasers." So we divided the labor, and 20 years later, we had designed the SuperCam.
SuperCam uses a system of lasers and spectrometers. With this telescope, we can obtain extremely detailed images of the surface of Mars. You can see details of around 20 microns per pixel when the camera is close to the ground. This is the first SuperCam image. These instruments conduct precise chemical and mineral composition analyses and can even detect the presence of organic material.
Lanzarote. Millions of years of volcanic activity have shaped this unique landscape. These geographic properties make it the ideal training ground.
This volcanic landscape really resembles the Martian landscape. It's even aligned along a fault like the red planet. And the oxidization is red, like on Mars. At first, Mars and Earth were very similar because they had the same origin. At one time, there were rivers which fed the lakes. And there was a magnetic field, or a protective shield that stopped the atmosphere from being eroded by solar wind. But it changed drastically about 3.7 billion years ago. The magnetic field from the planet's core abruptly vanished. Mars was so small that its atmosphere dissipated into space. The red planet became a freezer. A sort of ice age suddenly took over, and it never recovered, turning it into the dead planet it is today.
Has Mars retained traces of its past? The scientists hope so. The mission begins. The teams from the French National Space Agency, or CNES, and NASA are adjusting to Martian time. The days there are longer than on Earth. Each Martian day, known as a sol, lasts around 24 hours and 40 minutes, so the clocks have to be synchronized.
The mission has started. We have a reference period of 3 years. If the rover fails before that, then we have also failed.
On board, dear. And over the next time, you have about 9.5 feet, or sorry, 9.5 megabits.
Another thorough check to make sure all the instruments on board are working.
Our rover has an auto-nav system, so it can self-drive on the surface of Mars. Driving on Mars isn't that easy, right? We don't have a map, we don't have a phone that we can just say, hey, send me in that direction. So what the rover does is it takes pictures in front of it. It actually looks 5 meters ahead, and so that way it can actually drive from 200 to 300 meters a day autonomously. So it will drive itself. We can say, hey, at the end of the day, just drive in that direction for an hour and a half, and we'll see you tomorrow, and it will do that.
There is a time delay in communicating with Perseverance. Although the signals travel at the speed of light, it takes them a number of minutes to reach the rover. A command from Control Center. Then, millions of kilometers away, Perseverance starts moving. At night, the rover remains stationary. It transmits the information collected during the day to Earth and receives a program with tasks to complete the next day.
Each point is assigned coordinates, so when we tell the rover to target a point, it knows exactly how to turn its head to fix on the point we want. Then it sets 5 points in that direction with a laser, with infrared, and the camera.
She was very quick to get everything done, and I suggest we release her.
First, we ran extensive tests for 3 to 4 months. We made sure the arm was working properly, if the wheels were okay, if the head turned correctly. Then we checked if SuperChem could fire its laser twice. then the green laser, then toward the sun. And not at the sun, but at the sky. We learned how to use our instrument.
Notre instrument.
Supercam even captured a Martian solar eclipse for the first time, produced by the moon Phobos. Finally, operations could begin. The first job was to study the Martian soil. The rover landed on Jezero Crater, a huge depression created by a meteorite. NASA chose it from hundreds of other locations because it was the most likely place to find fossilized traces of past life.
We chose the Jezero site because it's a very old impact crater with traces of a delta. We have proof that a river once flowed into a lake there. Because to have a delta, you need a river and a lake.
The crater is about 45 kilometers wide, with a lake several hundred meters deep, enclosed by a delta. The lake held about 5 cubic kilometers of water and a layer of sedimentary deposit 70 meters thick.
Above all, we wanted diversity. Rocks from the bottom of the lake, from around the sides, and from the delta. So we chose a site with all this diversity in a concentrated area.
Perseverance at work. The rover's cameras have already shown that the area consists of very different geological layers.
One day, the camera person pointed out a hill in the distance, and we said, let's take a photo and use it as a reference point. When we saw the incoming data, we said, that's fantastic, we're at the bottom of a lake. So we had our first results.
The photos were revealing, but virtual exploration of the crater provides limited insights. So the rover made its way to the delta. For its own safety, it moved extremely slowly.
In 200 days, we moved about 2.5 kilometers, so only a dozen or so meters each day.
Enough to work at leisure, but not enough to explore the huge Jezero crater quickly. A little more speed was needed. Ingenuity, a small helicopter, was brought along precisely for such tasks.
Ingenuity is a technology demonstrator. There's 3 challenges to proving that your helicopter can function on Mars, right? Atmosphere is one of them. The atmosphere of Mars is 1% the density of Earth's. So a very, very thin atmosphere. The other 2 aspects, though, is the temperature. It gets very cold, negative 90 degrees Celsius overnight. The third aspect that's different from Earth is the gravity. It's about 1/3 the gravity of Earth. The way we test that here at JPL is we have a chamber about 5-6 stories tall. And in that chamber, we were able to balance the atmosphere, the environment, the temperature, and the gravity of Mars here on Earth.
Ingenuity weighs just under 2 kilograms. Its 2 counter-rotating rotors turn 10 times faster than those of a conventional helicopter on Earth.
For me, one of the most difficult moments on Mars is the day that we dropped the helicopter from the belly of the rover, where it was attached, down to the surface of Mars. I was in charge of those activities, and it was, I can tell you, incredibly stressful to make sure that our little friend was on Mars carefully.
Popped 3 meters off the surface of Mars, hovered for 39 seconds, and then came back down. We had that first flight. There were 4 remaining to round out our 5 total in our 30 days. And thankfully, at the end of those 30 days, Ingenuity was still healthy. The Perseverance team and NASA decided there's value here in continuing to fly on Mars. Ingenuity can act as a scout. We can fly to a cliff wall. We can dive down into a cave, right? We can go to very high altitude and loiter, or do a lawnmower pattern over a region of interest, for example. Ingenuity today is already providing reconnaissance for the Perseverance rover.
Sent ahead as a scout, Ingenuity sent high-resolution images to help Perseverance find its way to the Delta. On its 26th reconnaissance flight, Ingenuity even found the burst heat shield and parachute from the rover's landing. The route was clear. Now Perseverance could tackle its real mission, the search for traces of life on Mars.
We weren't looking for some macroscopic animal roaming around. That would have been easy. No, we were looking for traces of life that already existed on Earth at that time, and maybe on Mars. Primitive bacteria.
Michel Vizo is a veterinarian and works as a scientific consultant for the French space agency CNES. He is one of the world's leading experts in exobiology.
When we talk about extraterrestrial life, we focus on the simplest microbiological form, microbes. So if we find bacterial traces on Mars, we've found a new form of life. If we find a concrete trace of life, even fossilized, that is evidence of another life form in the universe. That's what we're looking for, even if it doesn't lead to Martians.
There was a period of 500 million or perhaps even a billion years when conditions on Mars were suitable for life. But was that enough for life to actually develop? I tend to think so, because chemical traces prove that 3.7 billion years ago, life emerged in Earth's oceans. I would like to believe that the same thing happened on Mars. And if life developed on Mars, where is it now?
Où est-elle aujourd'hui?
After a 5-kilometer journey, Perseverance finally reached the Jezero crater delta.
If the origins of life evolved from some prebiotic chemistry, then it most likely would have been in an environment of carbonates and clay minerals. So these are primarily what we're looking for.
We think that certain organisms living in very particular places on Earth today could also develop in certain microenvironments on Mars.
Purificación López García specializes in microorganisms that thrive in extreme environments. The hydrothermal Dalal area in northern Ethiopia is certainly one of the most impressive examples of a biosystem where life seems impossible. But despite extreme temperatures and acidity levels, single-celled organisms can be found in some areas.
At the edges of Dalol, there are ecosystems sustaining life, particularly archaea. These are unicellular microorganisms, like bacteria, particularly well adapted to very high temperatures of up to 120 degrees and extremely fluctuating pH levels. Studying these extramorphiles lets us better define conditions in which life could have appeared and persisted in extraterrestrial systems. If life emerged on Mars that could survive under such conditions, it could effectively exist in these systems as well, provided there was liquid water and an energy source.
Unlike the Earth, the Martian crust has never been reshaped by plate tectonics. This allows Perseverance to examine very old clay minerals. If there was once life on Mars, these minerals might still contain its components, like nitrogen or carbon.
To find intact organic molecules, it's best to dig a little deeper. And the rover's core can drill holes several centimeters beneath the surface to penetrate rock where they've been protected for millions or even billions of years.
Perseverance took its first sample of soil that might contain traces of organic material.
I would argue that sample catching system is just as complex as the rest of the rover. It has to be able to take sample cores from the surface of Mars, process them, put them in the tube, and then pass that tube to another robotic arm inside the rover that then takes pictures, does some certain analyses of those samples, seals them, because the samples are going to stay on Mars for a long time, and then it has the ability to deposit those sample caches on the surface of Mars.
We hope these samples will one day come back for lab analysis. To conduct a detailed sediment analysis, we need a laboratory with electron microscopes and high-resolution chemistry. That's not possible on a rover.
Perseverance will only store some of the tubes, not all of them. So rather than make one big pile with all the tubes and risk losing them all if the mission aborts, we leave a trail of scattered piles, like Hansel and Gretel leaving a trail of breadcrumbs.
They hope to eventually recover the samples from Mars and bring them to Earth for analysis. It's an ambitious project, especially because it's not yet clear exactly how this would work.
If you thought that collecting those samples and dropping them on the surface of Mars was already extraordinary and hard enough, eventually we're going to want to go bring those back. And so the teams here at the Jet Propulsion Lab and at NASA are already working on thinking as to how we might want to do that.
That's the first time we're going to launch something off of another planet. And then we have to bring it back home here to Earth and bring those samples back home safely and keep them contained. There are any number of challenges here that kind of dwarf anything we've done before.
The space flight system for the return mission should be ready in a few years. Researchers are already working on the new assignment.
These tubes will be recovered by a European-built rover, which will gather them with an arm, put them in a basket, and deliver them to a rocket, which shoots the container and its tubes into orbit around Mars.
This rocket will probably need its own lander. It will need to land very precisely near the tubes. It won't work if it lands 100 kilometers away.
The sample retrieval lander has a concept that we're working on right now, which allows the rocket that's going to take those samples from the surface of Mars to space to be thrown up in the air. We toss the rocket up in the air and then fire it. It's kind of like an air launch. And that's really the biggest advantage, is that we don't have to deal with any kind of erection system, right, to put the rocket in some kind of position that we want.
The rocket is almost 3 meters long and weighs 400 to 500 kilograms. You fire it in the air, the rocket ignites, and it's gone before it can come back down.
Once the orbiting sample canister, that OSS, is up in Mars orbit, we've got to find it with the Earth Return Orbiter. Remember, we're looking for something that's kind of basketball sized. That's pretty difficult, right? It's not a very bright thing. It's not very big. And we're going to have to find it from, tens to hundreds of kilometers away.
Putting a small white balloon into orbit around Mars and catching it with an orbiter? Not easy.
So we start by looking for the other parts of the rocket that have gone with it, that are bigger. The upper stage of the rocket has a radio on board with a beacon that will kind of scream at us every now and then, telling us where it is.
The captured container gets loaded into a space capsule, which returns to Earth 6 months later.
If all goes to plan, Martian rocks will one day be transported to Earth. It is crucial to ensure the samples are not contaminated by organic molecules brought by Perseverance from Earth. Though the risk is low, the consequences would be devastating.
The first space explorers in the 1960s remembered one thing: their own predecessors' lack of caution. The spread of disease following the exploration of the New World is a dark chapter in human history, and that contagion went both ways. Biological contamination of a Martian life form would be irreparable. The same is true in reverse. What would happen if an astronaut was contaminated by an unknown Martian species? What would you do with them? Could they be brought back to Earth? Or leave them there forever? Should they be brought back to Earth, but put in confinement for the rest of their lives? This is the stuff of science fiction movies.
A huge number of questions remain unanswered, but the ultimate goal remains. One day, humans will fly to Mars. But how can they survive there and return to Earth?
So for Perseverance, in addition to establish whether there has been life on Mars in the past, one of the other goals is to prepare for the eventual coming of humans on Mars. And so we have a few instruments on board that allow us to prepare for that. There's the META instrument, which is a weather station. It allows us to understand weather patterns on Mars, not just wind, but also dust, pressure. There's a ground-penetrating radar called RIMFAX that allows us to understand the structure of the ground below us. If we're ever going to build anything on Mars, understanding the Martian regolith is really important.
Jean-François Clairvoy is a French engineer and astronaut. He has been involved with 3 NASA space missions and knows how important remote projects are before the first humans travel to Mars.
We need to be able to remotely fly to and return from Mars before doing it with humans. That's why this test mission with Perseverance is important for deciding if we conduct a human flight to Mars. But to do that, you need to be able to mine as many local resources as possible for eating, drinking, breathing, and supplying the return trip. So everything doesn't need to be sent from Earth.
It is impossible to land on Mars carrying 30 tons of material, including oxygen, and stay for several months. But Perseverance is already helping to solve the problem.
Perseverance is not just studying Martian geology, it's preparing Mars for humans. The rover is carrying a small box the size of a car battery called MOXIE. It weighs 17 kilograms and converts the Martian atmosphere into breathable air.
There is less than 1% as much air on the surface of Mars, but that air is 95% made up of carbon dioxide. So within each carbon dioxide molecule is an oxygen molecule combined with carbon. So the job of MOXIE is to take those apart.
MOXIE sucks in carbon dioxide from the Martian atmosphere and passes it through an electrolyzer, which separates the oxygen and releases the carbon monoxide. Then, the oxygen atoms combine to form breathable oxygen molecules that can be inhaled.
Now, you or I would take 20 to 30 grams an hour just to live and to go about our business. So far, MOXIE has run 8 times on Mars and it made a little more than 50 grams of oxygen, which means it would keep us alive for a couple of hours. We hope with a larger version of MOXIE to make all that oxygen in situ to support a human mission on Mars.
Humans will discover a lot more than robots once they land on site. Artificial intelligence is quite sophisticated, but it only does what it's programmed to do. A robot will never shout, "Oh, look!"
Oh, regarde!
I long for the day when humans, with robots and cutting-edge scientific tools, will be able to answer the question of extraterrestrial life.
The question of alien worlds and extraterrestrial life haunts philosophers, theologians, and now scientists. Are we alone? There are 2 distinctly terrifying possibilities. One is the fear of being completely alone. In some religions, that's difficult to accept.
Our dream is to go to Mars one day, and I hope it will come true. That's the challenge of the 21st century. But this dream cannot be used to justify the idea that what we do to the Earth doesn't matter, because there's a planet B. No, there's only one Earth, and we need to take care of it. It's just about exploring another planet, and that's hard enough to do.
I don't know who named it Perseverance, but I think that's one of the most important qualities of a great researcher. Perseverance could be used to name basically any scientific program.
Perseverance will continue its search for life on Mars. The lone robot is not just exploring. It will also help make one of humanity's greatest dreams come true: taking people to Mars.
It's in the clouds. All I do is dreaming, facing the stars. All of them are blinking, and I feel small. And I Ready, steady, go! Hajima! Ready, steady, go! Ready, steady, go!
The International Space Station is the ultimate extreme home.
Space is an environment where human beings were not meant to live.
The most expensive structure humans have ever built. Here, in the most inhospitable environment known to man.
The only reason we can go there is by taking technology to provide us with everything that we need in order to stay alive.
With no air, food, or water, 250 miles above the Earth, it's an epic engineering challenge.
We as engineers are having to figure out how to make systems that provide all those functions that Earth provides in a tiny little can.
To reveal how the engineers pulled it off, we're going to take it apart and uncover what's going on inside. How the International Space Station and its superstructure secrets will help our species reach other planets and beyond. Costing up to an astonishing $150 billion. This is an unprecedented home.
The ISS is an extraordinary feat of engineering because not only do you have to make this big environment that people can live in, which, you know, is non-trivial to do on Earth, you have to do it in space.
It comprises millions of high-tech components. There are 16 pressurized modules with living quarters, sleeping bays, an observation deck, and 6 science labs, all connected via airtight tunnels. There's plenty of parking for visitors, including spots reserved for Russian Soyuz capsules, and the ISS's lifeboats, which are on permanent standby in case of emergency. Unlike any other structure, the ISS has to provide everything its astronauts need. If it fails, they die.
A human being can only survive for 3 weeks without food, 3 days without water, and 3 minutes without air.
For humanity to successfully venture well away from Earth, astronauts will need to be self-sufficient. If the ISS can solve the challenges, it will prove humans can truly live in space. But before anyone can take up residence, the engineers behind the ISS had to get it into space. And it weighs a colossal 460 tons. The same as about 300 cars.
It would be great if we could just build the International Space Station on the Earth and then just blast it into space.
You couldn't just fly the whole thing up there in one shot. You had to take a piece at a time and assemble it together like Lego.
The ISS began life as just 2 modules that had to be connected in space. One built by America and the other by Russia.
The first flight actually launched in November of 1998. Hadn't been that long since the end of communism in Russia, and here we were building a joint Russian-US space station. So just the political milestone that represented was pretty significant.
7 Up presents Pakistan Ka food scene.
After the intense competition of the space race, it's suddenly all about collaboration. The orbiting Russian module is known as Zarya, which means sunrise. Next, the first American module, known as Unity, sets off inside the cargo bay of Space Shuttle Endeavour.
Liftoff of the Space Shuttle Endeavour.
Unity is now chasing Zarya through space at more than 17,000 miles per hour. Two modules from two superpowers are about to dock.
First thing we have to do is to open up the payload bay doors.
Can you imagine how important it is for these two modules to mate?
Unfortunately, before both modules were launched, engineers spotted a problem.
Not all the pieces got to be integrated on the ground before they were launched.
Neither Zarya nor Unity were originally designed for the ISS. Their docking systems wouldn't fit together.
The Russian hatches are all round, and our hatches are all square.
I mean, this is fundamental to the International Space Station, and what you have are two things that don't mate.
And so, what do? Well, you make an adapto.
This is the moment of truth. Latches on the inside of the docking ring finally make the connection and pull the modules together.
Houston Endeavour, we have capture of Zarya.
The International Space Station is born.
It was amazing. I mean, here we are. We got airborne. We had Unity in the bay. And when we left a functioning space station ready for the next module to come up.
In the 20 years that follow, engineers from all around the world join the project, building their own space laboratories and bigger living quarters. But every one of the modules was constructed on Earth, and it takes a supreme international effort to launch them all successfully into space.
It took a long time to build Space Station. We have to fly everything up, we have to connect all the modules, put them together. So that took over 40 missions. Modules came from all over the world. We have the US modules from NASA, we have the Russian modules, we have the Japanese modules and the European module, you name it.
And it costs around $10,000 to send every pound of weight up here from Earth.
So right now, we're in the Japanese laboratory. It's one laboratory out of many here on the International Space Station. This is Columbus, the European module. It has science experiments all over. You could see it looks a little bit crowded. Here we are in the US laboratory. Again, this is a laboratory with science experiments on all of the walls here. So we're going into the Russian segment. Be ready. You don't need a passport either. And what's cool about this module, it is actually the very first piece of the space station that came up in 1998. It's been occupied continuously ever since then. So if you think for 18 years, there has always been a human presence in space.
Today, the ISS is enormous. By far the largest space station ever created.
It's actually big enough if you have a good pair of binoculars, and when it's flying over, right overhead, you can actually see it. Normally you look at a satellite and it's just a little dot, but the ISS is big enough that you can actually see it as an extended object.
It's so vast, in fact, that it would dwarf Times Square. At an astonishing 357 by 240 feet, it has more living space than a 5-bedroom home. But the larger the International Space Station becomes, the larger a very obvious issue becomes, too. Air. In space, there is none.
It doesn't provide a life support system for us, air, oxygen. And so if we have a home in space, we need to provide all of that.
The average adult breathes close to 4,000 gallons of air per day. With a crew that can be up to 9, the ISS must supply a huge amount of it, And it's not coming from outside those windows.
Their very survival really depends on the things that we provide them. And you're also having to deal with the fact that at any point in time, if one of your systems fails, you have a very limited amount of time to either get something from Earth or to get back to Earth as quickly as you can.
In a crisis, an emergency supply of oxygen can be sent up by rocket. With technological advances, spacecraft can now rendezvous with the ISS in 6 hours, if everything goes as planned. But even when a cargo delivery is successful, there's a price to pay. The cost of each mission is colossal, almost $200 million.
It's expensive to bring a kilogram of anything up to the space station. And to spend all that money just to bring up water and oxygen would be an incredible waste.
The ISS needs to make its own air.
The oxygen on the ISS can come from a delivery from Earth, and then they're stored in tanks. But the ISS is also capable of generating oxygen on board.
On Earth, we take air for granted. In space, each astronaut must be supplied with 1.85 pounds of oxygen per day, 365 days a year, to avoid suffocating. In the very heart of the ISS is an unassuming machine about the size of a trash can. It's this that holds the secret to keeping astronauts alive. Incredibly, it generates oxygen from nothing more than water.
So what happens is you have some water, you feed some electricity through that water, and the electricity will split that water into hydrogen and oxygen.
The oxygen comes off as bubbles at the positive electrode, the hydrogen at the negative. But again, being in space turns something that's straightforward on Earth into a major engineering challenge. The bubbles of gas won't come out of the water.
In your high school chemistry lab, the gas just bubbles up to the surface because the gas is lighter than the water, and therefore it goes up. Gas is not lighter than liquid in space because gas doesn't have any weight and liquid doesn't have any weight. So you produce gas bubbles and they just sit there. And what we generally do is we centrifuge it. So you spin it all around, and the liquid, being denser, it doesn't weigh anymore, but it still has mass. So it's denser, and it goes to the outside, and you can then separate the liquid from the gas.
The hydrogen gets thrown away, gets pumped into space, and the oxygen is used for the ISS air supply.
There's enough capacity on board to generate 5 to 20 pounds of oxygen a day. More than enough for the crew. In the extreme environment of space, making air is just the first challenge. The ISS has to keep it, but it's under constant threat of a breach in its hull.
There is so much space junk up there now.
There's the potential for it to puncture the outer wall of Space Station.
I was taking pictures out one of the windows, and it was a nice clear window. I came back sometime later to take another picture, and there was a great big ding in the window, about a 5/8 of an inch in diameter from a micrometeorite impact. And we had to take pictures, close-up pictures, send it down to the ground, and it had to be analyzed to see whether it was going to be a threat when we entered.
If you pop a hole in Space Station, the atmosphere is going to leave very, very quickly.
No atmosphere means no oxygen, and the consequences of that are obvious. So how does the ISS deal with the threat of colliding with meteorites?
₹235 में बने 1 लीटर नेस्ले बुनियाद आयरन प्लस, बेहतर जिंदगी की और भी मजबूत बुनियाद।
The International Space Station is the largest man-made object that's ever orbited the Earth. And it's racing around our planet at 5 miles a second. But on board, that's hard to appreciate.
How do we sense speed if you're in a car, for instance? You know, you have the road noise, you have the wind going by, you have billboards or trees going by your window. None of that exists in space. The only way you get a visceral sense of how fast I was going is, you know, you're going over the Pacific Ocean, and then 10 minutes later you fly over New York, and then 10 minutes after that you're flying over London.
If the ISS was orbiting closer to Earth, we'd all see how terrifying its speed is. It would cross the US from coast to coast in just 10 minutes, lapping the Earth more than 5,500 times a year.
But it's actually traveling at 26,000 kilometers per hour, or 17,500 miles per hour, so definitely be breaking the speed limit, right?
Speed on Earth can be incredibly dangerous, but in space, at the velocity the ISS hurdles, the consequences of a collision can be off the scale catastrophic.
Space debris is going by you at about 5 miles a second, so if there's a big piece of debris that happens to have your number on it, it's moving so fast you'd never see it.
March 23rd, 2012. Mission Control radios the crew.
And how about relative velocity? Any idea? Checking.
Something is heading straight for the space station.
The time of closest approach of this fragment of space debris is 11 minutes from now.
No one knows how big this object is.
Well, you do what you're trained to do, and even though you got woken up in the wee hours of the morning, you know what the reason is.
The crew must prepare the space station for impact.
Can you see it? Yeah.
You go through and you close every single hatch on station, which takes about 45 minutes.
Yeah. That's from which direction? Yeah, we don't know.
The hatches can withstand a sudden loss of pressure that would come from the hull being breached.
Coming up on the 6-minute mark.
If there is a puncture, any loss of air could lead to a serious emergency.
Coming up on the 3-minute mark until the time of closest approach.
The crew takes no chances. They head for the escape vehicles.
We floated into our Soyuz spacecraft with initial preparations for undocking if space station were to be hit.
1 minute from PPA.
And you just kind of hunker down and hope it doesn't hit you, and you just sit there and wait.
Looks like that's it.
Fortunately, this time it's a near miss. But the ISS cannot rely on luck.
The International Space Station is designed to work in the low Earth orbit, which is full of space debris. A lot of space junk is human-made. You know, they are things that we have put up there, satellites largely.
NASA has identified more than 500,000 orbiting objects that could pose a risk to the integrity of the space station's hull.
Luckily, most of the stuff that's big enough to hurt us we can track. There are a few objects up there which are too small really to be tracked well, but they're big enough to do damage.
The ISS is constantly bombarded. Most of the debris is tiny, but even a half-inch fleck of paint could inflict the same damage as a motorcycle crashing at 60 miles an hour. To be a viable home, the ISS has to be able to take the hit without losing all its air.
The ISS basically has a bulletproof vest. So just like a bulletproof vest, which has different layers of Kevlar that can rip as a bullet enters it, The ISS has different layers in its outer skin.
The space station's skin is known as Whipple shield. The outer wall is made from a thin sheet of aluminum, less than 1/10 of an inch thick. Beyond that is a blanket of woven material and a further thin wall of aluminum. It seems too delicate to protect the ISS from a direct hit.
It turns out that a solid piece of metal does not offer as much protective power as if you cut that metal into very thin sheets, spread them out a little bit.
When there's an impact with a high-speed micrometeoroid, it hits the outer wall of the ISS and pulverizes. Some fragments pass through the first layer of aluminum, which disperses some of the energy. Then there are layers of Kevlar and Nextel, a ceramic fiber that's stronger than some metals. As the fragments hit this blanket, they break up even more and don't have enough energy to penetrate the hull.
It's kind of counterintuitive when you think about it, you know, that a whole bunch of sheets of aluminum foil could somehow give you more protection than putting them all together. But that's the way it is in space.
The Whipple shield has protected the space station from micrometeoroids for over 20 years. But it's ineffective against anything larger. If a large object on a potential collision course is identified, the only option is to move the whole ISS out of its way.
Space Command monitors most of the space debris that is out in orbit. They notify our mission control here at NASA. We look at that and we have a green zone, a yellow zone, a red zone.
Objects that fall within the red zone have a 1 in 10,000 chance of hitting the ISS. Too dangerous to ignore.
If we think that something is coming within the red zone, the space station can adjust its orbit and give itself a little boost to get out of the way.
Small thrusters change the ISS's trajectory, but using them is expensive.
Now these thrusters, you can think of them almost like tiny rockets, and those rockets are using propellant, and that propellant isn't infinite.
It all has to be sent up from Earth at a cost of $10,000 per pound of propellant. This brings engineers face to face with the greatest challenge of all: how to reduce the station's reliance on Earth. The ISS can't be self-sufficient if it relies on thrusters to move. But a clever trick hidden at its center means it doesn't have to. The International Space Station has a problem. It orbits the Earth every 90 minutes and has to be regularly reoriented. Using thrusters is one option, but that uses up precious propellant.
With the space station, if here's the Earth, we want to keep the station, usually, I mean, there are sometimes exceptions, but usually you want to keep the station in the same relative orientation towards the Earth so that the cupola is looking down at the Earth. And in order to do that, of course, the space station is going to be rotating once every orbit around the Earth.
What the ISS needs is a way to move that doesn't use propellant.
The solution for keeping the ISS in the right altitude and also on track in direction is to use gyroscopes.
This is one of the ISS's most innovative secrets. At the center of the sprawling space lab, there's a quartet of small casings, each about the size of a small cupboard. They're known as control moment gyroscopes, or CMGs. But how can they move a beast the size of a football field?
They're really, really clever in that you can change the attitude of station without firing any thrusters.
The 4 CMGs are mounted on a truss near the very core of the ISS. Inside each casing is a flywheel, spinning at 6,600 RPM. The flywheels create a lot of angular momentum, and simply by changing the RPM, or tilting the plane they spin in, they transfer that momentum to the ISS, and the whole thing moves.
If I were sitting here in a chair and I had a gyroscope spinning around in this direction, and all of a sudden I put a brake on and slowed down the gyroscope, the chair would start to spin around. You know, I would slow the gyroscope around and then woo, I would do a big spin because that angular momentum has to be conserved.
So these 4 control moment gyroscopes can move the whole of the International Space Station, and there is not one single drop of propellant used in order to make that movement.
But they do use electricity, as does just about every piece of equipment on board. To supply the ISS's total power requirement, a whopping 75 to 90 kilowatts, engineers cleverly exploit the ferocious power of the sun. The station generates all its electricity for free.
The solar panels on the space station are absolutely essential because they provide all of the power that the station needs.
The panels have to be enormous, which would have made them impossible to transport had NASA engineers not come up with a genius way to get them into space.
What's really impressive about the solar panels, not least their size, around half an acre per array, but the fact that they are actually folded. And then once they're in space, they were able to be unfolded. Now that's an amazing thing to do in space.
Together, they can generate 120 kilowatts, ample for all the ISS's needs, and the equivalent of powering 40 homes.
In order to maximize the power you're getting, you have to keep the solar panels continually pointed at the sun, which means as the station is moving, the panels have to turn.
And so we have gimbals. If there's a solar panel, we can gimbal this direction, and then we can gimbal this direction.
One of the ISS's greatest engineering triumphs, it's been generating its own power for over 177,000 hours and counting. That enables round-the-clock air conditioning, fundamental to astronaut survival.
This cannot go down. It's not like a power cut in our homes where, we can get a torch or light a candle or something. If this goes down, astronauts will die.
As a USP expert volunteer, I help solve complex medication challenges. Join me and apply to amplify your impact with USP.
When the ISS enters the shadow behind the Earth, the temperature can drop to below anything ever experienced on our planet. Without the protective cocoon of the space station, the ferocious cold would kill astronauts in a matter of moments. Conversely, when in sunlight, the temperature can soar.
Temperature and managing temperature on the ISS is very important. If you imagine the extreme temperatures that you can get on the ISS if you're facing the sun or not, could be plus 250 degrees or minus 250 degrees.
So you have these huge temperature extremes simply because of being sunlit or being in the shade. And it's something that you have to keep in mind when you're doing your engineering.